Our neighbor Mars fascinates us. It's a planet that is similar to Earth, but with some big differences.
Mars is rusty, dusty, frigid, and frozen. It ain't the kind of place you want to raise your kids.
Past missions suggest that Mars was once a very different world.
The Mars we see today has completely changed from the Mars of a few billion years ago.
If I had a time machine to visit Mars in the past, I would go in an instant.
Without a time machine to explore ancient Mars, we employ a team of high-tech robot investigators.
We've got an entire fleet of robotic spacecraft exploring the planet.
Working together, they dig into Mars's past to answer the ultimate question: did Mars once have life? February 2021. The newest robot investigator speeds towards Mars, the most advanced rover NASA has ever sent to another world. This is Perseverance.
The goal of the Perseverance mission is to look for signs of past life on Mars.
First, it must navigate safely to the surface of the planet.
Every landing has its own dangers. Because the rover must be autonomous, it has to do everything without our help.
Perseverance enters Mars's thin atmosphere at close to 12,500 miles an hour. And deploys a parachute.
Navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity.
The parachute slows Perseverance to 200 miles an hour.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars.
Still too fast to land safely. To prevent a violent impact, the rover must activate the sky crane.
When I first saw the sky crane concept, I thought, the engineers are kind of losing it. It seemed to me like a really crazy idea.
Perseverance activates its jetpack. Retro rockets slow the lander's descent to a crawl. Then, 66 feet above the surface, the sky crane uses cables to gently lower the rover to the ground.
Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
Step 1 in the search for Martian life: find evidence of liquid water. A good place to start is the 28-mile-wide Jezero crater.
Perseverance has landed in a crater called Jezero, and this looks like a place where there was liquid water in its past. And the reason we think this is because there's this beautiful delta deposit right in the middle.
Perseverance turns its high-resolution cameras onto a cliffside in the crater and discovers giant 5-foot boulders near the top. A clue to how they got there may come from the first probes to visit Mars.
One of the very first things we noticed about Mars when we first sent probes there with Mariner and Viking was that there were these huge channels on the surface of Mars. Looking at these enormous landforms, we realized that in some places on Mars, there may have been enormous floods, bigger than almost anything we'd ever seen on Earth.
Flash floods on Earth cause similar rock formations to those found in Jezero crater, suggesting that powerful, fast-moving torrents carried the giant rocks found by Perseverance and dumped them at the top of the cliff. Perseverance is just one member of an elite team of robots patrolling the ground and spying from the air. The Mars Atmospheric and Volatile Evolution Orbiter, or MAVEN, investigates Mars's atmosphere.
MAVEN smells really good. It smells the Martian atmosphere. It tells us what the Martian atmosphere is made of all across the planet.
Then there's the Mars Reconnaissance Orbiter.
As its name suggests, an orbiting spacecraft that images the surface of Mars.
The MRO's high-resolution cameras can identify surface features as small as a kitchen table. And joining the orbital crew, the European Space Agency's Mars Express. With its ground-penetrating radar, it searches for evidence of subsurface water. And on the Martian surface, a group of high-tech landers take a closer look, including the team's quake specialist, InSight. This lander probes deep beneath the surface to discover how Mars's interior shapes the planet over time.
The InSight lander on Mars has a really simple concept. You land a spacecraft on the surface anywhere on Mars and then just listen for Marsquakes.
And 300 miles south of InSight, veteran rover Curiosity is exploring the Gale crater.
The mission goal for Curiosity is to look for habitability, and so that's environments in which life as we currently understand it could exist.
Curiosity searches for evidence of calmer, more permanent water in Mars's past. Investigating layers of rock at the base of Mount Sharp, a 3-mile-high mountain in the middle of the crater.
The rock layers start way up at the top of Mount Sharp, and they move progressively downward, and basically we're going backwards in time till we get to the very bottom. And the very bottom is actually really old.
Mount Sharp was built over millions of years, layer by layer. The rocks at the base of the mountain date to 3.5 billion years ago. These rocks are made up of very fine layers and could only have been formed in calm water.
These sedimentary layers were formed when Gale Crater was a lake, and sediment settles out and you get these beautiful layers.
Curiosity explores more of Gale Crater and discovers rounded pebbles like those we find on Earth.
When you see a rounded pebble on Earth, you know that that got rounded in a river channel. Some of them used to be angular, but their angles all got knocked off by being rolled and rounded and moved by water. So we're very excited when we see rounded pebbles on Mars.
The rock layers and rounded pebbles tell us that over 3 billion years ago, Gale Crater was a lake fed by rivers.
It was so exciting to understand liquid water in the context of Gale Crater, where Curiosity is. And that's just because what we see there is this long-lasting freshwater lake. And that's not like anything else we've seen on Mars before.
Imagine standing on the edge and looking out at this big, beautiful blue lake shining in the distance. What if there were just a whole array of craters filled with water off in the distance? It would be so beautiful.
And a good place for life to evolve.
Mars was a nice place. It was probably more like Earth is now, so it wouldn't surprise me if it supported life. We're talking microbial life. We're not talking, Marvin the Martian or anything like that, but life still is life.
Any water Mars once had is now long gone. To stay liquid, water needs warmth and atmospheric pressure. While robot team members Curiosity and Perseverance work the Martian surface, 8 probes orbit the planet, searching for clues about Mars's ancient wet history. Leading the pack is MAVEN. Its mission? To solve the mystery of Mars's lost atmosphere.
Today, the atmosphere of Mars is incredibly thin. It's only about 1% the atmospheric pressure here on Earth.
The weight of gas in an atmosphere pressing down creates pressure. And that pressure dictates at what temperature liquids boil.
Here on Earth at sea level, the boiling point of water is about 212 degrees Fahrenheit. But up here in the mountains near Denver, we're at a higher altitude. We've got a lot less atmosphere pressing down on us, and so it boils at a lower temperature. Let's put a thermometer in here. There's 200 even right there. And that's a lot cooler boiling temperature than at sea level. Now, if you go to even higher altitudes, at 100,000 feet here on the Earth, the air pressure is about what it is on the surface of Mars. And on the surface of Mars, water will boil effectively ambient temperature. We wouldn't have to heat it at all. You just put a glass of water on the surface of Mars, and it'll boil and disappear away.
But the planet's surface tells us that dry Mars was very different in the past.
When you see things like river channels that probably took millions of years to carve, that gives you an idea that the atmosphere was once very, very different. It had to be thick to allow liquid water to exist on the surface.
To investigate what happened to that thick Martian atmosphere, MAVEN swings into action.
One of the main objectives of the MAVEN mission was to measure argon on Mars. There are slightly different kinds of argon. We call these isotopes. And basically it means that there's just an extra neutron in the nucleus. So there's one type of argon that's just a little bit heavier than the other type, just by one neutron, not by much.
High up in the atmosphere, MAVEN tag teams with Curiosity down on the surface. They measure the amount of light and heavy argon.
Now, what's special about argon? Well, argon is not very reactive. It doesn't really get involved in a lot of chemistry. It's not really absorbed by rocks, doesn't change much. Once it's emitted, it kind of hangs around.
And that makes it very valuable because it means it stays in pretty much its pristine, pure form through the history of the planet.
When the researchers back on Earth compare the readings from the two Martian robots, something doesn't add up.
With Curiosity on the surface, we see a certain ratio of heavy to light argon. And we expect that same ratio to exist up in the atmosphere. But with MAVEN, we see a different ratio. We see far less of the light argon than we do down on the surface. So something is messing with that ratio. The only thing we can think of that can mess with the ratio of argon is the solar wind from the sun.
The sun spits out a constant stream of particles called the solar wind. The wind is over 1 million degrees Fahrenheit and travels at up to 500 miles a second. When it reaches Mars, it strips away gases high up in the atmosphere.
The lighter the argon is, the higher it gets up into the atmosphere. That means that gets blown away, preferentially, by the solar wind. The heavier argon stays a little bit lower down and a little bit more protected. So when you look at the ratio in the atmosphere of the light argon to the heavy argon, it gives you an idea of how much has been lost over time.
MAVEN's data reveals that Mars has lost 65% of the argon from its atmosphere, and the solar wind continues to bombard the planet.
The atmosphere of Mars is being stripped away by solar radiation by 1/4 pound every second.
This rate of atmospheric loss leads to one conclusion. The solar wind robbed Mars of its once thick atmosphere, and with it, the planet's water. But a question remains.
We know that Mars's atmosphere was much thicker in the past, really similar to Earth's. So why is it that Earth's atmosphere is still mostly there, whereas Mars's has been stripped away?
Earth has a protector, a magnetic field that shields our atmosphere from the ravages of the solar wind.
The Earth's magnetic field is generated deep in the core. There are actually two cores. There's a solid inner core and a liquid outer core. And that solid inner core is delivering heat to the outer core. And as it does this, it causes convection currents.
The convection currents pull electric charges around and cause magnetic fields to fold in on themselves. We call this a dynamo, and this is what's capable of generating powerful magnetic fields.
The magnetic field forms a protective bubble around Earth that deflects the solar wind away from our planet. Did Mars once have its own force field? To find out, MAVEN homes in on some ancient volcanic rocks on the Martian surface. It detects faint magnetic traces.
Martian rocks, typically in the form of lava, become magnetic when the iron particles in the rocks become aligned with a magnetic field that's active at the time, and then as the rock cools, those things get frozen in place. That sort of freezes a magnetic field into place.
What that tells us that these volcanic materials were erupted at a time where there was a magnetic field present on Mars.
Dating the magnetized rocks reveals that Mars had an active magnetic field for almost 1 billion years.
This means that the atmosphere of Mars was protected for those 1 billion years. And if the atmosphere was protected, the liquid water was protected. And if that liquid water was a home for life, then that life was protected.
But something happened to bring Mars's force field down. To discover what, our quake specialist, InSight, is ready to burst open the mystery of the planet's lost protective shield. Robots are rewriting the history of Mars. Now, InSight probes the planet's interior. Its mission? To discover if the secret of the planet's lost magnetic field lies beneath the Martian surface.
InSight was developed with the world's best seismometer. This is a really precise, really delicate, really sensitive instrument. And it just was placed on the surface and started listening.
2021. InSight listens for seismic vibrations called Marsquakes as they travel through the planet's interior.
It's detected quite a few Marsquakes, but these were very small. But then it detected 2 much larger ones. And these were interesting. Not only were they more powerful, but they were coming from the direction of Cerberus Fossae, which is a very interesting region on Mars.
The magnitude 3.1 and 3.3 quakes came from Cerberus Fossae, a series of trenches that stretch for 750 miles across the Martian surface. Some fissures cut through impact craters that are only a few million years old. This means Cerberus Fossae must be younger. InSight teams up with the Mars Reconnaissance orbiter, flying hundreds of miles above. This eye in the sky spots an ancient lava flow spreading out over a 3-mile area. Dating of the flow reveals that it's recent.
The Mars Reconnaissance orbiter spotted in the Cerberus Fossae region some lavas that appear to be about 50,000 years old. This is crazy young for Mars.
Mars has been around for billions of years. 50,000 years is nothing. Humans were around on Earth that long ago, so this is really recent.
Looking closer at these images, scientists learn this explosion was most likely a violent pyroclastic eruption.
A pyroclastic flow is kind of like taking a soda can and shaking it up and opening it up, right? There's dissolved carbon dioxide in the liquid, and when you open it up to the atmospheric pressure around it, that gas expands rapidly and you wind up getting a face full of soda. Imagine now that your can of soda is 5 miles high and 3,000 or 4,000 degrees.
The Cerberus Fossae eruption was really pretty big. was a 20-mile long fissure that opened up, and then a huge jet erupted out of that. It probably went tens of miles up into the sky and then blanketed an 8-mile region all around it. Based on the fact that we had these 2 Marsquakes recently, plus the evidence of the volcanic eruption just 50,000 years ago, I mean, now we cannot say that Mars is dead. We have to say Mars is active.
A volcanically active Mars suggests its interior may still be warm. If it is, why did the planet's magnetic field die? InSight probes deep into the interior of the red planet using vibrations from small Marsquakes.
InSight uses these to kind of construct what the interior of Mars was like, because these waves bounce off different layers inside the interior of Mars in different ways.
InSight's seismometer builds a picture of Mars by completely redrawing the map of the interior of the planet.
It turns out the crust is thinner than we thought. It's only 12 to 23 miles thick. So there's this whole picture of Mars that is unfolding in front of us that is vastly different than we ever predicted.
InSight's new and improved layout of Mars reveals a 969-mile deep mantle surrounding a metal-rich core.
New analysis of data from InSight reveals the size of the core of Mars, and we haven't had this before. It's so exciting. It's about 1,100 miles in radius. This is a little more than half the radius of the body, which is pretty big and is much bigger than we expected for the size of the core of Mars.
Mars's larger core makes up about a quarter of the planet's mass, and InSight's journey to the center of Mars reveals another surprise.
We have always thought that the core of Mars was long since solidified and wasn't warm at all. And InSight is now showing us that actually part of the core is probably still molten, which is shocking.
There's a liquid core at Mars. I mean, this is crazy.
Data from past missions may help explain why Mars's core is still liquid. Scientists discovered high levels of sulfur in the crust.
Mars seems to have a bit more sulfur, at least in the surface, than Earth does. If we extend that composition to the core and add more sulfur to the iron-nickel core, that would actually reduce its melting temperature, making it possible for this core to be molten today.
We thought that Mars lost its magnetic field when the core cooled and solidified. A molten core changes everything.
Well, how can we explain this lack of a magnetic field at Mars, even though there's a liquid core? Well, in order to have a magnetic field, you need the fluid to be moving and rotating and convecting.
Over time, as Mars lost heat and cooled down, its core stayed molten thanks to the sulfur. But with less heat, there was not enough energy to power the churning convection of liquid metal that creates an electric current.
The convection in that core would have slowed down to the point where no magnetic field would be generated.
3.7 billion years ago, Mars's magnetic shield dies. The solar wind's relentless attack strips the planet of its atmosphere. As the atmosphere disappears, water on the surface gradually boils away. Since the first probe visited Mars in 1971, 16 missions have investigated the red planet from orbit, while 10 landers have explored the surface. They've revealed Mars may still be an active planet, one that once had the right conditions for life.
Mars used to be thought of as this dry, arid, inhospitable environment. And thanks to the recent Mars missions, we know now that it could have sustained life.
Could there be any ancient Martian water left hidden inside the planet today? MAVEN investigates by analyzing Mars's atmosphere for one of water's components, hydrogen.
The MAVEN mission is looking at hydrogen that's currently in the Mars atmosphere. This is a really important thing to study.
The gas is produced when the solar wind slams into Mars's thin atmosphere and smashes apart molecules of water into hydrogen and oxygen. Hydrogen molecules come in two forms: light, regular hydrogen, and the heavier deuterium. The ratio of the different types tells us about the history of water on the red planet.
It turns out that it's much easier to lose the lighter version because gravity just can't hold on to something that's light as easily as a heavier thing. So we expect that as time goes on, we'll have less and less light hydrogen and more heavy hydrogen.
So if we can measure the outflow of hydrogen from the Martian atmosphere today, and specifically whether that's light or heavy hydrogen, we can start to get some kind of idea about how much water has been lost from Mars, and therefore how much might still be there today.
2021. Scientists at Caltech analyzed data from Mars's rovers and orbiters to discover the ratio of deuterium to hydrogen in the atmosphere. They find less of the heavy hydrogen than expected.
If Mars had lost a lot of its original water out into outer space, we'd expect to find lots of heavy hydrogen left behind in the atmosphere. But in fact, what we found was that the ratio told us that Mars didn't lose much of its water upwards, and so maybe the water went downwards.
Where is Mars's water hiding? Some scientists think it could be stashed away in the Martian rocks.
When we look at a rock, we often think this is a really dry thing. There's no water in there. But in fact, there's often a lot of water in rocks, and it's because it's bound up in minerals.
We're familiar with this process on our own planet. But here on Earth, that water is released when our rocks are recycled through plate tectonics.
On Earth, when we lock up water into minerals, then those rocks actually participate in the rock cycle, which means that they're going to be buried by all the active tectonics happening on Earth. And they get transported into the mantle where they get heated up. The water is liberated from the mineral structure, and it gets sent up, usually through volcanism, back up into the atmosphere.
Mars doesn't have plate tectonics, so there's no easy way to free the water. But this trapped water in the Martian crust could potentially provide a good water source for future human missions to the planet.
If all that water is still there, this might give us a lot more opportunities for the future exploration of Mars. Having a lot of water trapped in the Martian crust could be useful for the first human habitats and colonies to use that water on the Martian surface.
Changes in the crust can drive these minerals to suck up huge volumes of water, equivalent to a global layer over 300 feet deep. Researchers estimate that as much as 99% of Mars's water could be locked away below the surface. And Mars hides water in other ways too. Enter the European Space Agency's orbiter, Mars Express. Probing 1 mile beneath the Martian South Pole, it finds a secret store of water.
Really excitingly, we've discovered a system of lakes beneath the Martian polar ice cap. Lakes of what appears to be liquid water.
Now, these lakes are not very deep. They're probably only a couple of feet deep, maybe in some places even a couple of inches deep, but they're quite large. Some of these are about 20 miles across. And there's even some suggestion that these are connected with channels, kind of a system of very shallow Great Lakes near the South Pole of Mars.
The Martian poles are the coldest regions on the planet. Temperatures can reach 200 degrees below zero.
So why is it that underneath this cold ice you might even find liquid water? Well, remember you're actually going down closer into the interior of Mars there, and so that's warm. It's possible that the geologic activity inside Mars is warming the ice from the underneath.
But heat from the interior of Mars wouldn't be enough to keep these lakes liquid. The secret ingredient may be salt.
If you've ever spread salt on an icy driveway, you'll notice that where the salt hits the driveway, the ice begins to melt. Salt water actually freezes at a much lower temperature than water that's fresh. So if it's salty water, it could actually stay liquid at lower temperatures.
We still aren't 100% sure that the lakes are completely liquid. Some scientists think they could be lakes of frozen clay. Until we have a rover that can explore beneath the poles, we won't know for sure.
The only real way we can tell for sure is to send some kind of mission that drills right down through that polar ice and samples what we find at the bottom.
Veteran crew member Curiosity explores the Gale crater. The rover's mission? To find evidence of whether Mars could have supported life. Los Alamos National Laboratory. Principal investigator of Curiosity's ChemCam, Nina Lanza, works closely with the rover patrolling Mars, 34 million miles away.
In many ways, Curiosity is like my first child. We had to take such good care of her while she was still here on Earth. But like all children, she had to forge her own path. And so we had to send her on her way to discover new things on Mars by herself.
ChemCam uses a precision laser that analyzes the chemical composition of Martian rocks.
We have a laser that we focus onto a target up to 23 feet away, and we vaporize a little material. And then we look at the light made by this vaporized material and figure out what elements are in the rock. Working with an instrument like ChemCam is really a childhood dream come true because I was always hoping to work on a spaceship, and today I work on a spaceship with lasers. How cool is that?
With their long-distance teamwork, Nina and Curiosity discover rocks with a shiny coating, laced with manganese.
One of the most exciting discoveries from Curiosity in Gale Crater was the existence of high concentrations of an element called manganese. And that's because manganese on Earth is very closely tied to life.
Could the manganese of Mars be linked to life forms? To investigate, scientists look at similar coatings called varnish on desert rocks here on Earth.
So I have an example here of some rock varnish, and you can see it's actually incredibly dark. It has a lot of iron oxide, manganese oxide, and clay minerals in them. And the rocks can sometimes have none of these things in the rock itself. So the question is, where does this coating come from?
Often we find microbes associated with the varnishes, and so possibly these microbes actually help fix the manganese onto the surface.
The age of these Earth varnishes may provide a clue to Mars's distant past. Here, they only appear after a significant event in our history, the creation of the oxygen we breathe.
A couple of billion years ago on Earth was the Great Oxygenation Event. Basically, the Earth's atmosphere did not have a lot of oxygen in it. It was locked up in minerals and chemicals. Well, some bacteria discovered how to photosynthesize light, how to convert energy from light into their metabolism. And via the chemistry of this, they wound up emitting oxygen.
The oxygen was poison to many life forms, so they died out. But others thrived, pumping more and more oxygen into the atmosphere. Oxygen reacts with the manganese, binding it to the rocks.
We don't really see these minerals until after the rise of oxygen in the atmosphere, so after photosynthesis.
For Mars to have these same manganese varnishes, there must have once been more oxygen in the planet's atmosphere.
Is it possible that Mars had a lot of oxygen in its atmosphere in the past and there were wee little beasties processing it?
And so the search continues, and Curiosity uses another piece of equipment to sniff out traces of past Martian life.
One of the key instruments aboard Curiosity is a piece of lab kit called a gas chromatography mass spectrometer, or GCMS. And all this really is, in essence, is like a very sensitive electronic nose.
Curiosity digs up some Martian soil and heats it in its portable chem lab. Like a robotic bloodhound, it sniffs the vaporized dirt and picks up the faint smell of a rare molecular compound.
What Curiosity discovered was a compound called thiophene. This is interesting because, at least on Earth, thiophene is often found in fossil material, in coal, in oil, as well as stromatolites or microfossils of ancient life in the fossil record. So maybe this thiophene we've now discovered on Mars is some trace chemical fossil of ancient Martian life. Or possibly it was produced by non-biological processes.
Curiosity is knocking on the door of finding the evidence for life on Mars. We haven't found life, but we've found the interesting bits that are pieces of the puzzle, the organic puzzle of life on Mars. And so it's getting us to that ultimate question, is there or was there ever life on the planet?
To help answer that question, scientists bring in pinch hitter Perseverance. The newest member of the crew has the latest tech, tools designed based on lessons from previous missions.
Perseverance is so important because it leverages all of the knowledge of the previous rovers, which set the stage for taking samples on the surface of Mars, searching for life, and setting up a place for humans to explore in the future.
Perseverance gathers rock and soil samples, testing some itself and leaving others to be collected and returned to Earth later.
Perseverance is just the first leg of a Mars sample return mission. So its job is to collect the samples and deposit them on Mars. Then the Fetch rover will come and pick these samples up and place them carefully in a tray. Then it will rove to the MAV, the Mars Ascent Vehicle, and then they'll launch it into orbit. Waiting in orbit is a catcher's mitt that will take that set of samples. It will package it in an Earth return vehicle, and then that will be sent back to Earth. We all are just wanting these samples back as soon as possible, but science takes time. Discovery and returning something back safely takes time and care, and so it's worth the wait.
We are just at the beginning of the Perseverance mission. We have so much to learn. But I think all of us would be so thrilled if we could actually find definitive signs of past Martian life. That would be incredible. I don't know what form that would take, but we're going to look for it in every way that we know how.
In Gale Crater, Curiosity detects a huge surge of methane gas.
The methane we've detected in the atmosphere of Mars is potentially very, very exciting. Most of the methane in our own air, in Earth's atmosphere, is biogenic. It was released by living organisms.
Curiosity's result is exciting because we know that this can't be ancient methane.
Methane is really interesting because it has a short residency time in an atmosphere, which means it breaks down very quickly. Whatever is making methane in Gale Crater is doing it right now.
Curiosity has detected methane many times before, but this is the largest amount so far. Question is, what created it?
Maybe this Martian methane is the first trace we found of Martian life. microorganisms living deep underground. Or maybe that methane is not biological, but geological. It's methane that's been given off by volcanic processes in the past. The frustration is we can't quite tell the difference between the two just yet.
All we can do is continue to sniff the air and document when and where we see it.
The picture becomes more intriguing when Curiosity detects oxygen in greater quantities than expected.
There's a lot more oxygen on Mars than we had suspected, which is weird in the first place. And the amount of oxygen is changing seasonally. There's something in or on Mars that is adding oxygen to the Martian atmosphere during the spring and summer, and then taking it away during the fall and winter. There is something that is actively controlling the amount of oxygen in the Martian atmosphere. What is that?
Most of Earth's oxygen comes from living organisms photosynthesizing, and it changes with the seasons.
We have normal, cyclical, seasonal variations in the amount of oxygen here on Earth because of life.
The most land mass on the Earth is located in the northern hemisphere. And so that means that during northern summer, most of the oxygen on Earth is generated. So there's a peak in oxygen during the northern summer.
So where is the oxygen on Mars coming from?
Oxygen is a known result of life, of photosynthesis. It's a biosignature, it's a sign of life. Is this a sign of life on Mars?
The atmospheric changes in oxygen and methane are a fascinating puzzle and a tantalizing hint of life.
Life on Mars explaining these changes in methane and oxygen would be incredibly interesting. So it's probably wrong. The answer is probably more boring. And not that chemistry is boring, but it's a little less interesting than life.
We Mars scientists, of course, are always very excited about seeing signs of maybe extant life on Mars, but we're going to require really big proof before we feel truly excited that we've made this discovery.
The army of robotic explorers continues to rewrite the story of Mars, discovering a once warm, wet world with the potential for life. Now, a new generation of robots, led by Perseverance, will dig deeper into the red planet's troubled past and its frozen present, and maybe hit the mother lode, life itself.
With every new mission to Mars, I hope that somebody really is going to find evidence that life either existed there in the past or maybe even still does now. And with all of these missions on many places on this planet, maybe now is the best time to actually answer that question.
Whether or not it's likely that Perseverance finds life on Mars, we have set ourselves up for success, and I am so hopeful that we get to finally answer that question, the big question. Are we alone?